Hello everyone and welcome to another video where today we will be talking about a channel that we have not talked about previously, which is Flat Earth and Coffee. With their video, What Are the Odds? Heliocentrism is Statistically Impossible. Now, I have not watched this video. I have gone to the about 3-minute mark until I realized that my microphone wasn't working properly. So yeah, let's have a look at it again. So far, it seems to be a case of a flat earther not understanding what a statistical process is, and the flat earther kind of not really having a glimpse on what is perfect and like in terms of where some of the numbers come from that they will be citing. But let's not get ahead of ourselves and have a look at the video.
Hey guys, welcome back to another episode of Flat Earth and Coffee. I'm your host, Bobby Thompson, and
Hello, Bobby Thompson. I'm Olaf from Olaf Does Astro. In case you should ever see this video, which first of all I'm very appreciative of, I am just about finishing my master's degree in astronomy. I will hopefully graduate in July, depending on when I get my last final grade in August. And I'm also almost finished, not as almost as the astronomy degree, but also almost finished with my master's degree in physics. Yeah, so let's have a look.
in this episode, we're going to be talking about all of the many statistical impossibilities that make the heliocentric model impossible. So let's jump right in. The first thing I want to talk about is the second law of thermodynamics, which
Starting off with a cracker, I see.
states as one goes forward in time, the net entropy, or the degree of disorder or chaos, of any isolated or closed system will always increase, or at least stay the same. So in essence, time tends towards chaos.
That's a reasonable explanation. I would say that the possible states of a system will, over time, always get to the ones that are the more disordered than before. As long as you don't get any energy from the outside, which is what the closed or isolated means. But yeah, I'm happy with that. Yeah, sure. The universe, by the way, doesn't violate this. A lot of people say, well, an explosion. Well, an explosion is kind of the definition of entropy, isn't it? First, everything was very orderly and very arranged, and then you exploded, and then everything's everywhere. So, I mean, yeah.
Or disorder. Now let's look at our first.
I thought there was an argument, maybe coming, but okay. Maybe not. Cool.
Statistical impossibility, which is the impossible timing of the sun, which I call the celestial Rolex or the celestial clock. There are 86,400 seconds in a day, right?
In a 24-hour day, not in a sidereal day. Important difference.
Right. In a geocentric model, it is the sun completing a circuit above the flat Earth, which gives us a solar.
No, well, that's in the flat Earth geocentric model, not the geocentric model. Geocentrists still think that the Earth is round.
Day, right? Which is 86,400 seconds. And I want to talk about how accurate that 86,400 seconds is. Let's compare that to an.
What do you mean how accurate it is? It's a definition. We defined one day to be this long. That there is nothing accurate about it. It's a definition, also made up definition. If you know. So what you mean? Let's compare it. A definition doesn't have a margin of error. That's just no. That's not how that works. Not at all how that works, my dude.
Atomic clock. According to popular mechanics, an atomic clock loses a second only once every several billion to 1 trillion years.
I've always thought it was a bit more, like every couple of million, but yeah, could be wrong.
Wow, man, that is like there's nothing on Earth that accurate. An atomic.
Well, atomic clocks are that accurate, and they are on Earth, so I mean, kind of.
Clock. 1 second in a trillion years. According to Time and Date,
yeah, that's more of the things that I knew.
Atomic clock can deviate 1 second in 100 million years. These are inconceivable ratios. What about NIST?
Inconceivable. Sorry, I loved that movie.
NIST, National Institute of Standards and Technology, accurate to within 1/15 billionth of a second per year.
That seems also about right.
These are. So what these should be, first off, if you ever read something like that and believed it, you don't have a scientific mind.
I beg to differ. It is difficult to talk about atomic clocks. Well, maybe let's hear the argument first.
All of that is bullshit. Why is it bullshit?
Because you don't understand it, I suppose?
Bullshit, because how can you make a claim like that without a source to compare it to. So what are you comparing your atomic clock to?
An actual argument. I like it. So the way that we know about the accuracy of atomic clocks is in an atomic clock there is a cesium. Usually it's cesium-133. There are other atoms, but usually it's cesium-133. There are a couple of cesium-133 atoms, and we know how the energy states, which is how excited the electrons of the hull of this atom are. We know very, very well how they behave when going from one state to another. And in atomic clocks, we induce the state. And we measure the kind of energy, I guess, the amount of energy that we get from a certain amount of these oscillations. And when it is done, they essentially just count how many oscillations it made, and the atomic clock knows that so and so many oscillations mean that was a second. And that's how we measure the second. This is how an atomic clock works, and the uncertainty or the deviation comes because we don't exactly know how sharp or how how energetic this transition really is. We know it very well, but not infinitely well. There is some margin of error with this measurement that directly translates to a margin of error in time. But this is a difficult concept because atomic clocks are doing this kind of calculations is not done in high school. We did it in second year of the bachelor's degree, could be even third year. No, second year of the bachelor's degree in entry to quantum physics and experimental atomic physics. So this is a advanced topic to explain it further than I just did.
Are you comparing it to a Rolex?
You don't need to compare it to anything really. You measure. You can very, very reliably through quantum mechanics calculate the energy time, kind of the how the energy of this one oscillation translates to time, and that's how we use atomic clocks, and it works absolutely brilliantly. By the way, just saying.
Are you comparing it to a Timex, to a Casio, to some digital clock? What are you going to compare?
To the clock on my nightstand, to be precise. Which is funny because it's run out of batteries, so I don't know how it's still working, atomic clocks, but okay, sorry.
Compare it to make that claim. How can you quantify that? You can't.
Of course you can. You don't necessarily need to compare it to something for this kind of measurement. I understand why you would think that, because this is a very intuitive approach, and credit where it's due, it is a proper argument, but atomic clocks work different in that regard. We're not using a stopwatch to measure another stopwatch, if that's what you think we do.
But every timepiece in the world is compared to the sky. The sky is what dictates.
That's not true.
Dictates time. Does man dictate time, or does the celestial clock dictate time?
The sky dictates the time of day, but not time. Important difference. Whilst they're related, because of course humans a couple of 100 years ago just thought, well, let's take a unit of time, like I don't know if they started with the minute or the second or something, but they just use a measurement of time that was dependent on some fraction of the time of day, which they measured from. You just arbitrarily define something. You could say, let's make up a unit and call it I don't know, call it a lip. Okay, let's say a lip. The pronunciation of the at the end is important here. Let's say a lip is 1/100th of the duration of a day. So we now know that the day has 100 lips. Yeah, it's as easy as that. And then you create subunits, ideally that work with thousands or hundreds for the ease of calculation, not of 24 and 60 or something. But let's continue.
I say it's the celestial clock, right? There's nothing more accurate than that. And
that's not true. The sky changes compared to an atomic clock quite rapidly. Still very slowly, but compared to an atomic clock, very rapidly.
Apparently, it's so accurate that atomic clocks can be within a 15 billionth of a second per year. Wow.
That's I need to hear that sentence again.
Dictate time. I say it's the celestial clock, right? There's nothing more accurate than that. And apparently it's so accurate that atomic clocks can be within a 15 billionth of a second per year. Wow.
The atomic clocks would be that accurate without a thing to compare it to. You don't need the sky for atomic clocks to be precise. And I'm not sure why you would think that they need each other. It's not why. That's not a thing.
Now, there are testaments to that accuracy. One of those is Konark Temple in India.
Hey, a sundial. I like him.
Which is a megalithic site that has several sundials, and it's claimed to have been built in 1250 AD, which would make it about 774 years old. Still accurate to the minute. Let's watch this video.
But that's not difficult. The sun only changes its kind of the duration of a day only changes by a couple of nanoseconds every year. I don't know the exact number, but just from that nanosecond, so 10 to the minus 9 per year, we have around 1,000 years. That means that we are way good. No worries. The time with that sundial can measure accurately has not even shifted by a second, and I don't think it can measure it to the second. It can measure to minutes.
Okay,
if it's good.
So I put finger in axle, but my shadow is there. 6, 7:39, 10:30. So plus the 10:30. So now time is 11 plus some 10. 11:10 होगा.
Amazing, yeah. Sundials, they work great for telling the time of the day, because that's what we created the time of day to be representative of a sun. You know, yeah.
Now there are many other videos of Konark Temple. You can just YouTube.
And it's not just I assume Konark, the guy sounded Indian. I hope I'm not being racist here, but in that general area, those are of course not the only sundials. There are others which also work nicely.
YouTube or any video site and check out Konark Temple, and you'll see them using this sundial to tell the time, and then they'll ask the crowd, hey, what time it is, and someone will look at their watch, and it's accurate to the minute. If you'll see, if you watch, that this wheel has a number of beads that go around it. Each bead represents 3 minutes, and the beads are big enough that you can break the bead into thirds. So still accurate to the minute, 774 years later.
Which is exactly what we would expect.
Now, what about Anthem Veterans Memorial in Anthem, Arizona? Every day at 11:11 a.m. it casts this image onto the ground.
Which is not difficult.
And it's perpetual, right? So that.
You don't know that. How long has this monument been there? Not even 100 years. You don't know if it's perpetual or not, because the time that you have measured this was so little compared to the amount of drift of the sun. It's ridiculous.
That testifies to the timing of the sun. The sun maintains a perfect circuit.
Citation needed.
Perpetually. That's impossible. No explosion can create that.
I love it. From something that is roughly equally distributed, if you add natural laws, you can get perfectly ordered systems, or perfect in the sense of as perfect as the solar system, which isn't. Well, the word perfect really has no meaning in that relation, but yeah.
But what about the movement of the luminaries, right?
They do move. I know what claim is coming. I have not watched this yet. I'm sure he will claim that all of the stars are stationary.
Well, if we do a time lapse of the pole star or Polaris in the north, and we just leave the camera there, and this long exposure will yield this photo right here.
And it also works in the South Pole, which, by the way, is really weird on a flat Earth.
Which is concentric circles. So we can't see any movement of the stars. And just to drive that home, there was a monument called the Georgia Guidestones, which was destroyed in July 26 of 2022, and it had this hole drilled in one of the monuments. In one of the stone structures. You could look through that hole and see Polaris every night of the year, as long as that thing was there. It was destroyed by someone, nobody knows who, but maybe that's the reason it was destroyed. Maybe.
I thought it was destroyed by conspiracy theorists who thought that this was kind of some satanic thing. Yeah.
Word was starting to get out. But
you know that. Okay, I'll come to this later. Let's finish the thing. I made a little presentation about this. Or I will make. I started for the first kind of couple of items. I will finish the presentation, that I will make about this topic, and then we'll have a little look at that.
Let's talk about the relationship of the luminaries now, not the concentric
Sure.
circles, which is one impossibility, another impossibility, which is the lack of parallax.
I called it.
So what is parallax? This is parallax. Parallax is when you see...
Kind of. Not the best example, but yeah, sure, you can see some parallax, for example, when you watch this body. In the next frame, it moved more in terms of angular velocity than the others.
Object in the foreground, as you're moving, move past the object in the background. That's what you'd expect to see
Seemingly.
if you watch Star Wars, Star Trek, Lost in Space, Buck Rogers, whatever sci-fi film we're watching. We expect to see this. Our brain tells us we should. But what do we get rocketing to the cosmos at 1.2 million miles an hour? We get this. We get stars locked in relationship to each other that instead turn as a whole unit, almost like the firmament.
Almost as if the Earth was turning and not the sky, huh? Okay.
So we don't observe parallax. What about
I
patterns
imagine
that we've observed?
The constellations is just the same. Yeah, constellations never change. I don't think we need to talk about that. I will briefly finish the presentation, and then we will talk about all of these topics. Okay, so here we are at my little presentation that I would like to have a few explanations on odds and a couple of things that I think are important in context to the part of the video that we have watched so far. So when we looked at what we have seen, what are odds? Let's say I will travel with the train today, and I usually have 2 cables in my backpack. Now they are very different cables, so this is but let's just suppose they would be 2 identical cables, just with different connectors, okay? And when I grab in my backpack, how likely is it that I will grab the correct one without any kind of mechanism behind it? Well, 1/2, right? I mean, each depending on which cable I need. It's 1/2 for my phone and 1/2 for my laptop. Okay. That is a statistical process. I have a 50% chance of grabbing the right cable on the first try. Now, because I don't want to be, you know, I kind of would like it to hit it with the first grab. That's why I put them on opposite in opposite bags of my backpack. This is not a statistical process anymore. I sorted them. They are in a very specific place. The question, what are the odds, is very out of place. There are no odds. This is not a statistical process anymore. Not stochastic, not statistical. I need to emphasize this, and I also need to emphasize for a friend here, Bobby, don't use statistics for non-statistical processes. Big surprise, I know. Yeah, so, yeah. Let's get into the content of things, time comparison. So, atomic clocks, they are very good at counting time. Now, they're very good at counting seconds, and, you know, due to our definition that 60 seconds are a minute, and so far and so on, we know really well what's happening. They measure the state, the energy state, or the excitation, you could say, state of a certain atom, of certain atoms. It's mostly cesium-133 as far as I know. Although I think I have read that you could do this with other atoms as well. I believe they used strontium way back, something like that. Could be totally wrong. Just in comparison, a atomic clock drifts by about 1 picosecond. That's pico is 10 to the minus 12 seconds a day. And this is again due to the uncertainty in the atomic energy level of the excitation state. Now with the sun is very good at telling the time of the day, because we defined the time of the day on the sun. There is in our garden, sorry for the interruption, there is what you call it in English actually, a buck, you know, a deer, was just hot tailing across our garden right now, and I can see this from my window. Wow, what a sight to behold. Okay, so sorry, back on topic. The sun is very good at telling the time of the day, because we defined the time of the day based on where the sun is, so not a big surprise there. The sun drifts by about, like the duration of how long the sun is up, drifts by about 60 nanoseconds a day. Now 60 nanoseconds, that's 10 to the minus 7, 60 times 10 to the minus 9, sorry I said 7, times 10 to the minus 9 per day. That's very little. I have calculated for this core example We'll look at it on the next slide. This, by the way, this shift is caused due to mostly friction, or like an imparted angular momentum caused by the tides, by the way, and it's not a statistical effect. Just saying, nothing statistical going on here. You could say that there are some statistics involved in measuring the time with an atomic clock, but that's about it, and that's very much not what he was saying. So the sun is a lot less accurate than the atomic clock. Just comparing these two numbers, 0.1 picosecond and 60 nanoseconds, there's a difference in there about 600,000. And since the Connaught Temple, right, since it was built, the time accuracy of it would drift by about 0.02 seconds. So you can still tell the time, and you will always be able to tell the time of day because we defined, right? You get that. So what can we say from that? This is very much in agreement with the globe model. Nothing impossible here, and it's a huge surprise. Unsure if it's me or if you can't see the thing as well now. It was supposed to. Yeah, I think my program is glitching out. I hope that that's not permanent. Yeah, so it's completely in agreement. Big surprise. And not statistical. Just saying. The Georgia Guidestones, I love it. I love it so much. The whole of the Georgia Guidestones is like a degree or something. Do you know how many stars you could see in 1 degree of sky? So many. I love it. It shows perfectly the way that flat earthers think. They think, it's pretty small, and Polaris is exactly in it. Okay. So what would you expect? When should we not be able to see it? Well, if you look at the actual numbers, well, Polaris moves by around 45 arc seconds every 1,000 years. So for it not to be visible in the Georgia Guidestones, it will take many hundreds of years. So that is not a surprise. It's also completely in agreement with the globe model and not statistical in any way. Just saying, I thought I'd mention this. Parallax. I love it. I love the claim when flat earthers say we cannot see parallax in the stars. Have you tried? Seriously. As an astronomer, this is such a funny, because you can disprove it so easily, and I will show you right after I reach the conclusion. By the way, parallax is not statistical. Just saying. So far, not a single statistical process, not a single phenomenon that is unexplainable by globe math, so by the globe model, or whatever you would like to call it. Have you tried, and this is a serious question, have you tried getting the answers to any of these questions from actual globe sources? Like beyond the first Google result? Did you look at that? Did you look at the stars don't move? And did you look at, like, did you try to find parallax measurements? It's extremely poor reasoning and investigations, which, yeah, big surprise. Okay, and now we briefly show you how to find parallax. So, you said that, well, we can't find parallax. I completely disagree. For that, I would highly recommend you use SimBad, the website by the Strasbourg University, which is one of the best sources that we in actual, when I sit in my office, or what used to be my desk in the office, and I ask myself, I'm curious, how much is the parallax to this star? I go to SimBad. I enter the name of the star. Let's say we take Alpha Gruis, right? Oh, would you look at that? There's a parallax here, milliarc seconds. Oh, that's strange, but that can't be true. Let's have a look again. Let's take Beta Gruis. Why not, right? Oh, would you look at that? There's a parallax. Oh, well, that's unfortunate. Let's take Alpha Pisces. If I can, I hope I wrote that correctly. Would you look at that? There's a parallax here. Wow. Okay. That must have been coincidence again. Let's look at. Oh, I don't know. Pick a star. Oh, would you look at that? Polaris also has parallax. Well, that's a bummer. Now, not every source in here will have parallax. For example, the objects I work currently with, and that there will be a paper out very soon. This one has one, for example, but I searched one earlier. I think it was 660 exactly, and they haven't measured the parallax for it yet because it's pretty dim. So yeah, but almost all sources that you will find in there will have a rather reliable parallax. Yeah, just in case if you're interested, the number here in the square brackets is the uncertainty of the parallax, which you can see is a lot lower than the actual parallax value, so you know that we are sure about this. So I have provided ample source here for particularly the stars don't move, which I find is the funniest statement a flat earther can make, because it's so blatantly wrong, and it doesn't take any time whatsoever to discredit that statement. Great. With that, I think this is quite enough for one video. I will see you in part 2 then. Until then, have a nice time. Goodbye!